Okay, so welcome to Module 4 on memory. And today we are on Lecture 3 within this module. We will be covering process new memory allocation. When a process has started, it will dynamically try to get more memory. And that's what we will cover under memory allocation. The Linux kernel provides system calls to allocate memory to processes that are running. And these system calls are break, sbreak, mmap, mlock, munlock, a few more. These are the big ones. And then on top of that, the C library has a few more additions that add on top of this functionality and make it a little easier to consume these API calls. So the process, by making one of these system calls, can go to the kernel, and the system call in the kernel will actually allocate, deallocate, extend a memory area. We discussed memory areas. And then what happens is at that point, it does not really allocate a physical page. The on-demand memory allocation is where the physical page gets allocated later on, the physical memory, which is also known as the resident memory. When the CPU gets to an instruction that is trying to access that memory, the CPU will throw a page fault. That is when the kernel has a page fault handler and sees, oh, okay, so you are actually using this memory. Let me allocate you a page frame. That's how memory management works in an on-demand memory management style. This way, the kernel avoids processes just using up memory because they're asking for it, rather than they get memory when they're using it really. Now, we have seen the memory chart of a program. And from the bottom, the text segment, the global data segments grow. From the top, the stack comes down, and in the middle, we have shared libraries, memory map files, and anonymous memory regions. So there are two ways that the program can actually get more memory. One of them is you ask for an increase in your heap segment, and a program's heap segment ends at the point that is called a break. That is the end of the program memory. Now, it's only the end here because you only asked for the end for so long. You can ask for this break to be moved up. When you move it up, you will have more virtual memory allocated to you. And then when you use that virtual memory, you will get physical memory from the kernel. The other way is you can actually allocate a new anonymous memory using mmap. And that way, you can actually get a memory not in this heap region, but in another region in the middle somewhere that you specifically choose to operate. And say you can usually use your heap region, but if you want a separate one, maybe because you want to create that in a shareable model, and we will get to that with other processes, you can use a memory map region for that. So we will be covering these ways of how you can allocate more memory to a dynamically running program. Because we do go with examples, what I have written is a small program here that will do a malloc. Now, malloc is the C library function call that internally will make the system calls to increase the memory. There are two ways malloc operates, and in this program, I use both of them. When you ask for a small amount of memory, and the specification for malloc is less than 128 kilobyte, malloc will just extend the heap by increasing the break point. If you want more than 128 kilobyte, then malloc actually creates a separate memory region for you by making an mmap call to get another anonymous region. And in this program, I'm going to make a small request to malloc, and I'm going to make a large request to malloc. And then I'm going to see how that plays out, and we will look at our memory maps and what we are actually getting allocated here. So this is how you allocate memory. Here I run my program. I have a shell script that actually executes and prints the memory maps along with running the program. So I can see here in the printout that the heap address for the small segment that I wanted is different than the heap address for the large malloc call that I did. And the large malloc call actually are widely different. The heap area, then I printed out the maps, and I can see that the small malloc call gave me an address that is inside the heap area, and the large one gave me another address for which I can see there is another virtual memory area that has been created. And I have listed both of these on the left side, the heap one, and below that, the other memory area where the large malloc address allocation is. So this is just interesting to know that how malloc will give you memories in both of these ways, depending on how it wants to allocate and the logic inside of it. Now, the other detail that I have looked in is the S-maps, which is a memory map detail for the new segment or the memory area that was created. And I can see that it created it at a size of 148 kilobyte. The RSS for that is 16 kilobyte. And the interesting parts here is that I did not ask for 148. I did ask for smaller than that, but there is some additional management piece that malloc will add. And it is using 16 kilobyte in anonymous RSS reference already from that memory segment. The other thing you can find out about running programs is when you generally won't get into the memory areas, memory segments, day to day, you're not going to get into that detail. It was interesting for us to look how it operates, so we are under the hood on how things are running. When you want to look at program level memory characteristics, you can actually look at the proc/pid/status file, and we used status for our CPU information as well. So status gives you more information than for memory, but I took out the pieces that are relevant to memory here, and we can go through that. So here what you can tell is there are some numbers that start with VM, and VM or names. VM prefix means virtual memory. Then you will also see the RSS. RSS is the resident set. That is the memory that is actually in physical frames in the RAM. So the VM peak is the max virtual memory that this process was allocated. The VM size is the virtual memory size right now, which happen to be both the same on this one. So it is at its peak. Is there any locked virtual memory? No. And we will get to locking in a little. Is there the high water mark? Some are not that significant, but high water mark means how much of the resident memory did it get to allocation at the high level. And the RSS is at 348 kilobyte here. The high water mark is also at 348. So the physical allocation that we have is actually the same as the high water mark, the maximum physical allocation that happened on this one. So VM RSS is the total amount of resident memory that this process has. RSS anon and RSS file, we discussed that file memory is one that has a file backing, and anonymous is one that does not have a file backing. So anonymous memory is 72 kilobytes. This is where your heap is. This is where your stack is. This is where you can create memory regions that we just created in this program using malloc. RSS file is where you have a file-backed memory. This is where the program code is. And so we can see that we have 276 kilobytes of file-backed RSS, 72 kilobytes of anonymous RSS, and both of these add up to be the total VM RSS that we can see at 348 kilobytes. Then you can go further down and it tells you the virtual memory on the data segment, 320 kilobytes, the virtual memory of the stack that we're using, executable, VMEXE, VMlib is shared libraries, VMPTE is the page table entries. We're taking 32 kilobytes of virtual memory on that. So 32 kilobytes will mean it is 8 pages of 4 kilobyte each. And then VM swap, and this is another detail we will get to later if it has used any swap virtual memory. So that's an interesting bit of information you can get from this one. Usually when I look at program memory, I go to what's my resident set on this one, and maybe anonymous file level distribution. Total virtual memory gives you a lot more data across the board as well. But at times not hugely relevant because we don't care about what's not in the RAM as much. So delayed on-demand memory allocation is one way to get memory allocation, and usually the way you will get it. You can, in scenarios, use an mlock call where you want to pre-allocate the memory. So when you call mlock, the operating system will pre-allocate memory for you. And here I have a small mlock program where in mlock I do a malloc, but after that call I also do an mlock call. And then on the right side I have printed out the status, and I can see now that the VM that is locked is 132 kilobytes, and I created 1024 times 32 times the size of an int, and that is 32 KB times 4, which is 128 kilobyte, and then there is probably another 4 KB of extra space that is used in the malloc operation. So that's how the 132 kilobyte space is locked up. Now, the other parameters are the same, except that in this case we have locked our memory, additional memory, which will be available in our RSS resident set as well. Let us now look at other ways to allocate memory. An interesting way that you could use memory is to use memory mapped files. And what memory mapped file does is usually you will go and open a file descriptor, read something out of that, and then store it in your heap. And you can bypass that where you really want to work on the file data directly. And you can do a memory operation to do that, and the Linux kernel behind the scenes will manage mapping your memory to the file. You are able to operate with simple memory pointers. You can avoid the whole file IO calls that you need to do. The kernel memory manager will handle it for you. The process calls memory, and behind the scenes is the file interaction that's happening. There are the calls mmap and munmap available for you to do those operations to map memory, and then when you don't want it later on to unmap that memory segment. Mmap read. This is the case of a file read operation, and what we will do here is we will open a test file that has something inside of it and then read it by opening up a memory map to that file. I do pre-allocate and pre-write into that file just in the test case, which is not the important part here, but the important part is the part where I open up the file which has the data in it. I map it to a memory element in here using mmap, and then I read the data using that memory. And behind the scenes, the kernel is going to get the data from the file. Now, when you read, there are a few parameters you pass. I am passing prot read here as a protection flag and map private. Prot read means it will allow me to read that memory mapping that I'm opening up. Map private means that it is just going to be private to this process. And usually for read, it doesn't matter. You will just open it at my map private. And there are other things you can do that extend behavior here. You could do map populate as well, and that will pre-read file pages into memory. That is kind of like mlock, except that it doesn't lock it. And you can also do map locked here. That will pre-read the file pages as well as lock them, so you don't need to run an mlock after that. So there are a few more flags that you can pass and enhance the behavior of how mmap works for you. Just keep in mind when thinking of locking memory, you should ideally let the kernel do its job, because when every process would lock its own memory, there's no way the kernel can manage anything anymore, because everybody has just locked their data sets. So it's for special programs where you really have a need like that, because otherwise you want to let the kernel do its job. As we run this program, there are other characteristics from this program that you can see, and that is you can see the memory mapped address. I also have the status written out, as well as on the right side, I detailed out the mapping from the smaps file for this one. And that is where I can clearly and distinctly see that this test.read file is actually in my memory regions now available. It has a size of 4 kilobyte. It has a resident size of 4 kilobyte as well. And it is available. And on the bottom, you can also see the VM flags. It is available in read mode to me. So these are all interesting things just to prove that what I did in the code and what I see in the results is all matching up. Similarly, you can also do a memory map file write. And for that, I have written a file write.c program. And what this does is it will open up a file in write mode and then pass it to the memory map. And then I will write something to the memory map, and that the kernel is going to write what I write into the memory map into the file. If you choose map shared, you will actually write down to the file. If you choose map private as one of the flags that you pass instead of map shared, it is just going to keep it in memory and not write it back. So if you wanted to write back to the file system, you have to use the map shared option. Otherwise, you just have a write that's private to your process only. So here is the data from the map write, and similarly, I can see on the right that I do have a region opened up for write. I can see that in this case, the VM flags are read and write as well. So I open it because I opened it up in that mode, and that protection flag of prot write as well. And then I have the status of my program on the left-hand side, which I've generally written just to compare things. And on the top, I can see the results of the print statements, and I see a hello world from the memory mapped file that I'm writing to. Then the other thing is memory mapped is usually for files, but you can also open up anonymous memory writing with this feature. And it could be typically used when instead of heat, you want to open up an anonymous memory region, and maybe you want to share it with some other processes. Then you can actually not share everything else, but share like just this one memory mapped region. So in this case, what happens is memory mapping is implemented the same way as with a file backing, except that it writes a file backing to the in-memory file system instead of a physical disk-based file system. And so you will lose the data when it's gone, but you are able to manage just memory frames through this memory mapping for anonymous. So here's a memory map anonymous, and we are going to just write a hello world to it. So we open up that memory mapped anonymous region with protection read and write, and I open it up as a map shared and also a flag for map anonymous. Now, when I do that, I do not need to pass a file descriptors because there's no file descriptor in the backend. And then I do a string copy operation, just test that I'm able to write to it, print out the end results from that address space, and just view the detailed regions and maps that are created through this operation. So I can see now on the right side, I have a map, and that is an anonymous memory map. And I can see that in the non-mapped file information, there is no file information. It just says dev0. Dev0 is a zero page that gets assigned to an anonymous region until it has written something to it. And when you write to it, it'll just give you a frame to that anonymous region. And on the left side, you can see other statistics about the process and the fact that the process ran. I can see it on the printout. There is a memory mapped address, and we have hello world from a memory mapped anonymous or from an anonymous memory mapping. Additionally, when you run processes and allocate memory, you are able to limit certain sizes of allocations by process, and you can put a max on. You can look at the user limits that are available. A few of these are on memory, like the max locked memory that you can keep, and this way nobody just gets to keep too much of memory locked, but administratively someone can assign higher levels to you for that. You can have a max memory size that you could use, You can have a max stack size, and some of these have defaults. Some of these are unlimited. Stack size is defaulted to 8 megabytes of stack, and that helps prevent just recursive operations that can go on and increase the stack. Virtual memory can be limited as well. And on the right side, I have just written parameters on a process that is running on where a process is with these actual limits. And you can see these, I didn't change any of the U limits, but I just put it out there. So you can see what the defaults are on the left. You can see the limits that are on the right. And if you wanted for a user process, you could change the U limits by making them so. So we covered new memory allocation through malloc, which does break. Then we did memory mapping to a file and memory mapping with anonymous, and just looked at all the results with the memory maps that get opened up, with the RSS resident segments, with virtual memory. So we covered things around this area today. In the next one, we will cover more things that the kernel does on the backend while all processes are running, to give a more optimal experience to all processes. Okay, thank you.